mathematicians have got around this, and there's a couple ways we can do it. I'm going to go with graphic and not equational, because I think equational scares people off. I'll give you the equation later if you want it, but I'm going to start with the graphical because I think students like this more. So we need some colors. Need some colors. Blue, maybe green. I'll find green later. So here's how mathematicians have gotten around this problem. They start. Instead of having it in a T-table, which is too hard to fill out, they draw a number line. They draw a number line. With arrowheads on the end, that gives us an idea of continuum. Now, when we graphed Max's guesses over there, and it looked like a bell curve, that was a number line too. But there were discrete points, 0, 1, 2, 3, 4. The problem with a number line is there really aren't discrete points. What's the next number up from 2? What's the next number up from 2?
3. It could be 2.01.
It could be 2.01. It could be 2.001. You guys are answering discretely and correctly. The next number up from 2 is 3, discretely. But what's the next number up from 2 continuously? And it's a trick question. Because Janelle said it could be 2.01, and I said it could be 2.001. And Kelly's going to say it could be
2.0001.
and it could be 2.000. You can always put another 0 in there and get it that much closer. So the question is, how close can you get? And the answer is infinitely close. And that becomes an issue when you're trying to actually write those down. So mathematicians said, to hell with that. Let's draw a line. And as you draw the line continuously, you cover all those numbers, don't you? You've covered the real numbers, the coverage of the real numbers. Beautiful. What number's in the middle? Trick question. Good answer. What number have we decided to put in the middle? 0. 0 divvies up the real number line very nicely. Because it puts what over on this side? Positives. And over on here? This sounds like, it feels like you're in second grade again. I apologize for this. But yeah, this is what you learned back in the day when you learned to count. When you learn about positive and negative numbers. 0 is the great divider. Is it even or odd? It's even. It's an even number.
Because one's odd.
Because one's odd, and negative 1 is odd, and 2 is even, it all remains even. There we go. That was a bad question, I apologize. So now what I'm going to do is, I'm going to put a few whole numbers here. 1, 2, 3, 4, and I'll label that 1, 2, 3, 4. Now, what I'm trying to imply here is, there are numbers between them. Half, pi, let's see, we just looked at one earlier today. Square root of 2.5. That's what we looked at earlier today with the standard deviation of max square root of 2.5 right there. Down here are negative numbers, negative 1, negative 2, negative 3, negative 4. And those go on forever. Negative 5, negative 6, negative 7, negative 8, 4, 5, 6, 7, 8, 9, 10. They go on forever. What those are, statistically, are standard deviation measures. We're going to call them, this is where statisticians stepped in and go, we like your number line. Can we borrow it to talk about continuous variables? And mathematicians said, sure, go for it. So these numbers right here, these numbers that are right here, that's like it should be a red mark. These numbers right here, we're going to call them standard deviations. Also known in the statistics world as z-scores. Also known in the statistics world as z-scores. I don't know why they're called z-scores. I wish I did. I don't. I haven't done the research into them yet. But they are called z-scores. So when you see 1, that's 1 standard deviation up from 0. 2 is 2 standard deviations up from 0. 3 is 3 standard deviations up. Negative 4 is 4 standard deviations down. That's what I like about calling them standard deviations is, what does it imply the average is? Average is 0 when you place it like this. When you place it like this, your average, mu, is going to be 0, and your standard deviation, sigma, is going to be 1, because each one is one more jump of standard deviations. Just FYI, this is called the standard normal distribution. Keep that in the back of your mind for the next half an hour-ish. That'll take us right through until Thursday. We'll have some fun on Thursday with applications. So what we've taken care of so far is we've taken care of an analog to the x column of our t-table. That's where the random variables live. The random variables live down here. So if you do a study like we did with Max, and we were expecting him to land here, and he lands way down here, we start thinking that he's not average. And of course, that was father. That's pretty much what about saying, right? Poor kid. But we were assuming he was guessing, but he landed way down here, which means we don't think he's guessing anymore. So that gives us a reference point. If you hit 0, you've hit average. If you hit left or right of 0, that means you're skewed from average in some way. But the question now is, if this represents the position of the random variable, where are the probabilities? Where are the probabilities? In the discrete distributions, it was just the right column. You call it good. Hey, done. Where are the probabilities? For example, what's the probability to land at 0? Or 1? Or 2? Or 3? So let me ask you a question. Are we more likely to land at 0 or 2? 0? 0? Or will it land at 2 or 3? 1 or 2? -1 or 1? Nice. So you guys have a working knowledge of what the probabilities are going to look like, right? If we were to draw them all, what would it look like? It would be the bell shape. So what that bell is, let's draw it. Let's draw on top of this. What that bell actually is, let's see how long I can draw it. What that bell actually, it's not too bad, a little skewed. What that bell is a series of little tiny dots. How many of them? Infinitely many. Yes, there's more than you can count. And each one of those dots represents the probability of the z-score directly below it. So in other words, the probability that you land exactly at 1/2 would be given to you by that height right there, whatever that height is. The chance that you land at 0 would be given to you by that height right there. The chance that you would be exactly at 1.96262626262627 would be that height right there. That's how you actually calculate them. I'm here to tell you nobody does that. Because how many of them are there? It's infinitely many. Do you remember when I was showing you that, I'm not going to start the PowerPoint up because obviously it has had an issue today. But as we added more and more bars to the binomial, the bars themselves were getting shorter because there were more of them. Well, think about what would happen if you have infinitely many of them. Essentially, they shrink away to nothing, wouldn't they? So nobody does them in a case-by-case, piece-by-piece basis. What they do is they talk about the ranges. They talk about the ranges between values. So for example, you already know some of these. So this curve right here, what's the probability that you're within 1 standard deviation? You know the answer to this already.
95.
Of average. Average there. What's the probability that you're within 1 standard deviation from average? It's a number we haven't used in a couple weeks because we got away from bell curves a little bit because you start doing binomials, which sometimes are skewed.
Is it
65?
It's about the 2/3, 68%, I think is what 95 is 2 standard deviation. We'll get that in a second, Kel. So my question for you guys is, where does the 68% or 66, whatever it is, 2/3, where does that number come from? Well, the first thing you have to realize is, what does within 1 standard deviation of average mean? Well, what it means is, you go down and start at -1, and you go up and stop at +1, and you add up all the probabilities of every single number between -1 and +1. So you start at -1, then you move directly to its right, which is what? Negative something. Negative 0.99999 infinite number of 9s. And you add that. And then you go negative 0.9 infinite number of 9s, 8. And then you negative 0.9 infinite number of 9s, 7. Anybody get pissed off with the infinite number of 9s and negative number at the end? That's kind of ridiculous, right? But the idea is mathematically you can do that by simply doing something you learned in geometry class. Shade the area. If you've taken calculus before, this is called integration. Who's taking calculus? I think one or two of you. This is called integration. You're basically filling it up with an infinite number of infinite rectangles and adding those areas up. And it's really cool mathematics. If you want to see more, it's on that Richmond page if you need to help sleep. So when you shaded, friends, the entire region between -1 and +1, how much of the curve have you shaded?
68%.
The 68% we were talking about. You have now shaded 68% between -1 and +1. Mathematically, we can show you how that happens. Kelly's answered us the next one. What's the chance? Oh, so within 1 standard deviation would be 68%, or roughly 2/3, somewhere in that neighborhood. How about within 2 standard deviations? She told us that already, right? What's the chance that you're within 2 standard deviations? You know the answer to this already. We've been using it for weeks. 95%, Michaela. 95%. Why is this? Because if you take a different color, I don't think my green marker. I'll use orange instead. If you start at -2, +2, and you do the exact same thing, start at -2, go to +2, you're going to shade a lot of extra stuff. Whoops, you're going to shade your foot. You're going to pick up all that in the middle, it's in there too, and you're going to keep going and coming out to here, and that, what you just shaded, is entirely 95%. Let me ask you a question. What's this right here? Just this little orange piece right here? Think about that for a couple seconds. Don't just give me an answer right away. What area would be right here between -2 and -1? Think about it and raise hands. Let me see hands on that one. What area would, oh, that's okay. They can take that. They can take that. Let me see hands on this one. What area is between -2 and -1? Yes, let me see hands. I like this, I like this. We're doing some mathematics. Madeline, go! She votes for 13.5%. Tell me how she got that. Boom! We know that this is 95%, right? If we take 68% away from that, that leaves us with 27, correct? That means this plus this is 27%, which means each piece has to be half of that. Half of 27%? 13.5%. How about that, huh? So, what are you assuming about the curve, which is correct? That the bell curve is good, symmetric, like equal on both sides? It is. You guys already had that figured out weeks ago. Now, the beautiful part about this is it's predictable because there is an equation that governs it. There is an equation that governs it. The probability of any given z-score is equal, don't write this down unless you really want to, is equal to this. So, if you plug, oh, not an X, a Z. If you plug a given number into that Z and evaluate this expression, it will tell you how high the curve is. And then if you need it, okay, I'll go ahead.
Well, I was just going to ask, is it the same percentages as the bell curve?
On the left and the right, -1 or 1? Yes. Kayla asked a very good question. You see that Z squared right there? That takes the negatives and makes them the same as the positives. Isn't that cool? Maybe. I think it's cool. No, I think it's cool. It's all right. The beautiful thing, too, is it's an exponential function. It's e magical 2.718281828 raised to a power. That's why it has these asymptotes over here. It's got an asymptote here. It's also got an asymptote over here. Lydia, go! That is, it's root 2 times pi. Yes, it's divided by 2. Sorry. So if you need the equation, there it is. I guarantee you're never going to want to use it. Because in order to actually get the areas that we're doing, you have to do what's called integration between a start point and a stop point. And the problem is, if you haven't taken calculus before, that's mysterious and it's meaningless. Which is why I gave you another program that does these for you. If you look at the gifts that I gave you last time, there's one called STNormal. STNormal stands for Standard Normal. Again, I had 8 letters, so I had to tell me as I could. Fire that STNormal, I did 8 letters. Grab that one, and I want to show you how to use STNormal.